Hi, this is the last video of this playlist about the preparation of olefins. In this video, we'll have a look at the conversion of alkynes into olefins. As usual, by terminal alkynes or alkenes, I refer to compounds with a triple or double bond at the end of a chain of carbon atoms. Alkynes are mainly prepared by alkylation or arylation of terminal alkynes or by dehydrohalogenation. Unfortunately, alkynes are not stable and do occasionally explode upon heating. Terminal alkynes readily form copper, silver, and other transition metal acetylides, often in protic solvents and without the need of any base, and these acetylides can also explode. So take care when working with these compounds. In this presentation, I show you first examples of the partial hydrogenation of alkynes to olefins, and then of the alkylation, arylation, and finally acylation, carboxylation, and cyanation of alkynes to yield substituted alkenes. You are of course welcome to jump directly to the section which interests you most. When two carbon atoms form a triple bond, the hybridization is sp. The triple bond consists of two pi bonds, each formed by two atomic p orbitals, and one sigma bond, formed by two sp orbitals. Hybrid sp orbitals have more s character than sp2 or sp3 orbitals, and their energy levels lie lower. Alkynes are therefore more electrophilic than olefins and more susceptible to nucleophilic attack. Both terminal and internal alkynes are more acidic than alkenes and can sometimes be deprotonated or isomerized by alkoxides or sodium hydroxide. The sp carbon atoms are also sterically highly accessible. The hydrogenation of alkynes is therefore easy and generally faster than that of alkenes, and with deactivated catalysts, alkynes can be hydrogenated selectively to olefins in high yield. Alkynes also react with electrophiles, for instance with chlorine. Treatment with hydrogen chloride yields vinyl chlorides. What cannot be done is to prepare oxyrenes by epoxidation, also because oxyrenes are anti-aromatic and thus highly unstable. Then, as I said, the addition of nucleophiles to alkynes is relatively easy, and I'll show you some examples later. So, let's start with the partial catalytic hydrogenation of alkynes. Common catalysts are supported and deactivated palladium, platinum, nickel, or rhodium. Deactivation can be achieved with pyridines, quinoline, or with sodium hydroxide or other potential catalyst poisons. Partial hydrogenation of alkynes often yields cis-alkenes, but not always. Because of their high electrophilicity, alkynes also react with various metal hydrides, two metallated olefins, which may either be hydrolyzed or trapped with some other electrophile than protons. Alkynes can even be reduced to alkenes by alkali metals or zinc. Again, the resulting intermediates can be hydrolyzed or quenched with other electrophiles. Let's check some specific examples. Here, a propagyllic tertiary alcohol was hydrogenated to an allylic alcohol with a trace of palladium chloride in ethanol. One problem of tertiary propagyllic alcohols or amines is that the carbon-oxygen or carbon-nitrogen bonds are readily cleaved during hydrogenation. This did not happen here though. This here is an example of the selective partial reduction of a diacetylene with sodium. Only the terminal alkyne reacted. Benzylic carbon-oxygen bonds were stable under these conditions, but benzylic carbon-fluorine bonds were not. Low-valent titanium intermediates react with alkynes to titana cyclopropenes. In this example, the required titanium intermediate was generated by reduction of titanium isopropoxide with a Grignard reagent. Electrophilic deuteration of the titana cyclopropene gave a cis-alkene without decellylation. Hydroboration and protonolysis can sometimes also be used to prepare cis-olefins from alkynes. Here, a particularly sensitive iodinated alkyne could be reduced this way, without cleavage of the carbon-iodine bond. With the aid of platinum catalysts, alkynes can often be hydrosilolated stereoselectively to vinyl silanes. In this example, hydrosilylation and protonolysis were performed in one step, with the aid of a copper catalyst. No reduction of the nitro group occurred. The partial hydrogenation of alkynes with deactivated palladium catalysts, for instance the Lindlar catalyst, often requires careful monitoring of the amount of hydrogen consumed to prevent overhydrogenation. One alternative is transfer hydrogenation with some easily quantifiable hydrogen source. In this example, an amine was used as reducing agent, and mostly the cis-styrene was obtained. This is an example of homogeneous hydrogenation with a soluble ruthenium catalyst, mainly yielding a trans-styrene. No hydrogenolysis of the carbon-oxygen bond occurred, and also the nitro group remained unchanged. With an excess of benzyl alcohol and 20% of potassium tersbutoxide, diaryl alkynes can be reduced to trans-stilbenes, as shown here. A small amount of ruthenium carbonyl and a high reaction temperature were also required. Unfortunately, with aliphatic or terminal alkynes, the yields were much lower. This is an example of a typical alkyne partial hydrogenation with a Lindlar catalyst consisting of palladium on calcium carbonate deactivated with quinoline. A clean cis-hydrogenation was achieved, without any cleavage of the allylic CO bond or addition of ethanol to the electron-deficient alkyne or alkene. Propionic esters, like the starting material of this example, readily undergo Michael-type additions with all kinds of nucleophile. Nevertheless, a clean cis-hydrogenation was achieved here with zinc and formic acid. The reduction was catalyzed by 10% of nickel bromide. Okay, let's switch to alkylations of alkynes. A huge number of examples have been reported, both of hydroalkylations and of alkylations with the simultaneous formation of vinyl silanes, halides, or additional carbon-carbon bonds. As mentioned, even alkynes devoid of electron-withdrawing substituents can react with strong nucleophiles. Here the potassium enolate of propiophenone added to a terminal aryl alkyne when heated in DMSO. One alternative reaction pathway could have been deprotonation of the alkyne followed by addition of this anion to the carbonyl group to yield a tertiary alcohol. This alternative route becomes dominant with cyclohexanone or acetone, for instance. With other ketones, however, the alpha-vinylation shown here appears to be the preferred pathway. This example is similar to the previous one. Again, no tertiary alcohol or conjugated enone, but an allyl ketone resulted. In this example, however, the initially formed allyl cyanide isomerized to an acrylonitrile. Here, instead of an enolate, diethyl zinc was added to a terminal alkyne. An iron complex and 6% of ethyl magnesium bromide catalyzed the addition. No deprotonation of the alkyne occurred, and after deuteration, a high yield of trans-alkene resulted. This here is a rare example of electrophilic enantioselective aminoalkylation of an internal alkyne with an imine. Upon homogeneous hydrogenation, apparently a nucleophilic intermediate resulted, which added to the imine. Instead of enolates, also silylenol ethers can be used as nucleophiles to alkylate alkynes. In this example, the electrophilicity of the alkyne was enhanced with 10% of silver triflate and chlorotrimethylsilane. This is an example of electrophilic chloroalylation of a terminal alkyne with an allylic alcohol. Best results were obtained by lithiating the alcohol to facilitate its reaction with boron trichloride. Another intermediate was probably an allylic cation. The chloroalylation proceeded with high regio and stereoselectivity. Here a diaryl alkyne was metallated twice with a mixture of sodium and a Grignard reagent. The dianion was then allylated with allyl chloride and 10% of copper cyanide as catalyst. I'll show you now some examples of alkyne arylations. Both hydroarylations and arylation with simultaneous silylation or halogenation have been reported. This is a hydroarylation of a terminal alkyne with aniline. As catalyst, 5% of a magnesium salt was used, and the reaction proceeded under slightly acidic conditions. With a pKa of 9 in water, hexafluoroisopropanol is a weak acid. Similarly, also phenols can be vinylated with alkynes. Here, the reaction was catalyzed by rhenium carbonyl, but required a rather high temperature. yield and regioselectivity were high, but not the stereoselectivity. Also, electron-deficient arenes can react with alkynes. In this example, an aryl ketone added in high yield to silylated phenylacetylene. An iron 0 complex was used as catalyst. Similarly, aryl phosphine oxides can also be vinylated with alkynes. Here the reaction was catalyzed by a ruthenium complex and 20% of a silver salt. Yield and regioselectivity were excellent. Instead of arenes, also certain alkenes can react with alkynes and yield conjugated dienes. In this example, such a vinylation was catalyzed by an iridium complex in methanol. When terminal alkynes react with aryl halides in the presence of palladium 0, aryl alkynes are usually formed by the so-called Sonogashira reaction. With internal alkynes, oligomerization and Benz annulation is often observed. In this example, a disilane had been added, which led to the formation of a silylated styrene. Here, a Grignard reagent was added to diphenylacetylene, and the intermediate vinyl magnesium compound was chlorinated with a chloroimide. The reaction yielded mainly one stereoisomer. A similar reaction could be achieved in one step with the electron-rich mesitylene as nucleophile. In this instance, a trans-iodoarylation occurred. Let's now have a look at some acylations and cyanations. One strategy for converting terminal alkynes into enones is by addition of a deprotonated alkyne to an aldehyde, followed by isomerization to an enol. Imines or iminium salts can also be used for this purpose. These reactions do not require stoichiometric metallation of the alkyne and may already proceed in the presence of basic or acidic catalysts. Internal alkynes can be acylated with concurrent formation of a carbon-hydrogen, carbon-halogen or carbon-carbon bond. In this example, a terminal alkyne was converted into an enone by addition to an aldehyde. The reaction was catalyzed by 5% of a rhodium complex. No beta elimination of the thiomethyl group occurred. This here is a similar reaction with an imine as electrophile. In this instance, 20% of potassium terzbutoxide was used to deprotonate the alkyne and bring about the isomerization. Earlier I showed you examples of the conversion of internal alkynes into titana cyclopropenes with titanium isopropoxide and a Grignard reagent. These titana cyclopropenes are nucleophilic and react with a broad choice of electrophiles. In this example, acylation with a Weinreb amide followed by hydrolysis yielded an enone with high regioselectivity. Because no elimination of chloride occurred, the conditions cannot have been too alkaline. Internal alkynes can also be converted into vinyl anion equivalents with hydrogen. Here a diaryl acetylene was hydroformylated by treatment with hydrogen and carbon monoxide. A mixture of taurine sulfonic acid and iron and palladium complexes acted as catalyst. The reaction mainly yielded one isomer, without any cleavage of the carbon-bromine bonds. With an aniline instead of hydrogen as nucleophile, alkynes can be aminocarbonylated, as in this example. Catalysis by an acid was again required. Titana cyclopropenes also react with dialkyl carbonates, as shown here. In this example, a mixture of two isomeric acrylates resulted, together with 5% of the hydrogenated alkyne. This byproduct could probably have been avoided with a slight excess of diethyl carbonate instead of just one equivalent. Transition metal catalyzed cyanations can be difficult because cyanide tends to form stable, unreactive complexes with many metals. For the cyanation of alkynes, nickel complexes seem to be the most effective. In this example, instead of hydrogen cyanide or an alkali cyanide, isobutyl cyanide was used as the source of cyanide. The hydrocyanation was catalyzed by a mixture of dimethyl aluminum chloride and a nickel complex. The Friedel-Crafts acylation of terminal alkynes often yields either alkenyl ketones or chloroenones. In this example, mainly one isomer of a chloroenone was formed. This here is an example of iodoformylation of a terminal alkyne. As a kind of sophisticated carbon monoxide equivalent, trimethyl trifluoromethylsilane was used, and the reaction was catalyzed by copper iodide. During the reaction of terminal alkynes with copper salts, copper acetylides are always formed, which are easy to oxidize to conjugated diacetylenes. Thus, oxygen must be carefully purged from these reactions. Acyl fluorides are less reactive than acyl chlorides, but can still be used for the haloacylation of alkynes. In this example, an electron-deficient alkyne was rendered more nucleophilic by treatment with tricycloxylphosphine, and then acylated with a benzoyl fluoride. Interestingly, the intermediate phosphonium fluoride fragmented at room temperature into the starting trialkyl phosphine and the target vinyl fluoride. Despite the presence of chloride in the reaction mixture, no chloroenone was formed. Halogenated enones are strong electrophiles and tend to be vesicant, lacrimogenic, and often very toxic. In particular, low-boiling haloenones should therefore be handled with care. Metallic zinc can also be used to metallate internal alkynes. With a cobalt catalyst, 4-octine was first metallated and then iodocarboxylated with carbon dioxide and iodine. Mostly one isomer resulted. Even benzonitriles can serve as a cyanide source for the cyanation of alkynes. This here is an example of nickel-catalyzed cyanoarylation of 4-octine. Like in the previous example, a cis product resulted. With cobalt and zinc as catalysts, however, trans-cyanoarylations are possible, as shown here. In this case, a much larger excess of benzonitrile was used. No cleavage of the benzylic CO bonds occurred. As mentioned, the acylation of terminal alkynes sometimes yields alkenyl ketones, as in this example. Here, the acylation was catalyzed by palladium and further promoted by an excess of triethylamine. Let's have a look at potential side reactions. I've already mentioned some of them. Allylic or propargylic carbon heteroatom bonds are easily cleaved during reductions, in particular tertiary carbon heteroatom bonds. Then, in the presence of copper and oxidants, terminal alkynes quickly undergo oxidative dimerization. Because of their high electrophilicity, alkynes can add water, alcohols, amines, thiols, and many other nucleophiles, often under surprisingly mild conditions. Alkynes with electron-withdrawing groups are excellent Michael acceptors, and it can be difficult to prevent their hydration or amination. Then, alkynes and acetylides can explode, for instance during distillation or drying. Some of the products described above are reactive and may already decompose during their preparation. For instance, when acetylene reacted with the potassium enolate of acetophenone, the initially formed allyl ketone isomerized to an enone. Michael addition of acetophenone gave a diketone, which was further converted into the bicyclic acetal shown here. Some metals can form carbene complexes upon reaction with alkynes. These complexes do sometimes react like carbenes and can undergo insertion or cycloaddition reactions, as in this example. Here are some more references which you can also find in the description of this video. For subscribers, I've also placed a PDF version of this presentation under the Community tab. This was the last video of this playlist about the preparation of olefins. There are many more strategies than those I've covered here, but most lack general applicability or are way too expensive to be of any relevance. Maybe I'll discuss them in some future video. So just stay tuned and thanks for watching.